Today's lesson is going to focus on the concept of equilibrium. Equilibrium occurs in chemical reactions that are reversible. So many chemical reactions can be reversed. Some can a little bit more easily than others. And it'll happen when the potential energy of your reactants and the potential energy of your products are relatively equal, and there is not a really large activation energy barrier to overcome. So when this happens, you will know that you are in a reversible reaction situation, or you're on your way to achieving equilibrium by the arrow that we use. So we're going to start to see double arrows being placed in our reactions. And when we see that, we know it's a reversible reaction, easily reversed, and that we're going to achieve equilibrium. Equilibrium occurs when the rate of the forward reaction is equal to the rate of the reverse reaction. So we know how to calculate rates of reactions. These rates would be the exact same value, same speed with which the forward and the reverse are occurring. When this happens, the concentrations of all of your reactants in your products will remain constant. This does not mean that they're equal, so that their molar concentration, for example, are not all the same value. They're just all constant in that they're not changing, okay, once equilibrium is achieved. Equilibrium will tell us the extent of a chemical reaction, because remember, we're still talking about reactants making products, but we know that those products start to react and then go backwards and form reactants. So the equilibrium will tell us that the forward reaction is occurring at 50% completion or 90% completion. And there are numerical values that will tell us, how far the reaction is proceeding. When we reach equilibrium, you really can't tell, okay? There are no visible changes. So if there was a change in pressure, so for example, if you're creating a gas, remember that the concentrations of everything are going to stay constant. So you actually will not see a change in pressure or color or pH or a change in molar concentration within the system. But we know that that doesn't mean nothing is happening. We still have this forward and reverse reaction occurring. It's just that everything remains constant. Here's a nice visual to kind of explain what is happening as we approach equilibrium. So initially, you're going to have some amount of reactants that are going to collide with each other and begin to form products. So here in our second step here, we see we only have one reactant particle left, and we've made all kinds of products as a result. This is telling us that we're on our way to achieving equilibrium. If there were no reactant particles left at all, then that is a one-way normal chemical reaction that you have been studying, and the reaction is done. There's no reactants left, or the limiting reactant is all used up, and the reaction is over. However, in a reversible reaction, there will always be some amount of reactant left over and some amount of product left over. And so what we'll see here in the second step is that these product molecules or atoms, they now start to collide and they start to reverse themselves and create reactants. And then the reactants start to collide and make more products. And then what will happen is that the rate of that forward reaction is going to equal the rate of the reverse reaction. And these concentrations that we see down here are going to remain constant. So they don't achieve a constant amount right off the bat. It takes a little while for them to go back and forth, swing the rates back and forth until those rates are equal. And then once that happens, the number of particles or molecules of your reactants and your products will stay the same on either side of the reaction. Graphically, we can look at a concentration versus time graph and know when we've reached equilibrium. So here's an example of a reaction down here. This is the production of ammonia, which is a reversible reaction. And we see that we start off with some concentrations of nitrogen, quite a bit of hydrogen, and then we're creating our product. And the reaction right here, initially, this is at equilibrium. I can tell because the concentrations are all constant. They are not equal. There's a very slight chance that they actually could all be equal, but it's very rare. But I see that those concentrations are not changing. I have all three substances present, reactants and products, that's reached equilibrium. And we see it up here too in the graph. Then what they do is they add some extra nitrogen. And so the concentration of nitrogen will go up. It will react with some of our hydrogen, the other reactant, and it's going to make some more ammonia, which is our product. So we see some fluctuations right here in the concentrations, but again, there's this reversible forward and reverse reactions happening, and eventually the rates are going to end up to be the same, and then the concentrations end up constant again. Notice that they're not at the exact same spot as they were over here. That's totally normal. But the minute that we see those concentrations plateau, we know equilibrium has been achieved. So we've mentioned this already, but when we reach equilibrium, it's actually hard for you to know. Macroscopic properties, these are the properties that you and I could visually see, stay the same. Okay, so right here, for example, is a good example of equilibrium. So we have the rate of water entering into this container equaling the rate of the water leaving the container. And once those rates are equal, this water line should not change. It should remain constant. And again, it doesn't mean that nothing's happening there. We're getting new water molecules entering into the system. We have old water molecules leaving the system. But it's at equilibrium. And again, you wouldn't be able to know. It'll look like nothing's happening. And that's because the concentrations or the amounts of water staying the same. Some of us maybe at the mall have tried to go up a down escalator, okay? And when your rate of you moving equals the rate of the escalator going down, it will look like you're not moving. Okay, but it's because the speeds, right, of each of them are equal. And then again, it'll look to people that you're like stationary on that escalator when in fact you are moving and things are changing. You can also have equilibrium happening here in a container of water. As long as it's sealed, it has to have a lid on it. And then the amount of water evaporating gas molecules will fill up this container space here. And then once this gets saturated, then these gas molecules are going to start to condense and form water, liquid water. And again, you can achieve an equilibrium in this situation as well, where these evaporation rates and condensation rates are equal. And then the amount of water in the gas phase and water in the liquid phase, it would remain constant, not necessarily equal, but constant. So a couple things to know about equilibrium. It can only be reached in a closed system. Okay, so you have to have a lid on it. So here's an example again of our water in a container where the water here initially we put a lid on it. A bunch of it is going to evaporate and we're going to have gas particles fill up this space right here. We see them right now in this container as time goes on. And then what we notice will happen, right? Those gas particles are going to come out and go into the liquid phase while your liquid water molecules are going into the gas phase. Notice how the water line has moved, right? Because a lot of water molecules evaporated to fill up the space in here. But once we achieve equilibrium, this water line is not going to move. Okay, it's going to stay constant. And if we didn't have a lid on there, right, that water would just simply evaporate and all those gas particles would go into the atmosphere. So you have to have a closed system, especially on gas reactions, in order to keep all the reactants and the products contained. A couple other key points about equilibrium is that it can be approached from either direction. So typically we are going from reactants into products. And we'll usually start with, amounts of reactants and do some calculations from there. But just be aware, you could approach it from the product side, right? You could start with some products and have some amounts of those, and then work and try to figure out the amount of reactants that you have. So you can approach it from either side. Two types of equilibrium that we have: homogeneous equilibrium. All that means is that they are in the same phase, okay, reactants and products. Heterogeneous equilibrium, it means that they're in different phases. So here's an example of a precipitate, silver chloride. It does not dissolve well in water at all, but a small amount of it does go into its ionic form, and it does dissolve into water. And because those states are different, we would call that heterogeneous equilibrium. Take a few minutes and complete these questions. Once you have your answers down, find me and I will be happy to check them for you. And you can also consider this application of equilibrium with a bottle of pop, okay? So why might we want to reseal open bottles of carbonated drinks quickly? Okay, so here's the reaction, the main reaction that happens in a bottle of pop with carbonic acid and water and CO2. So consider why it's beneficial to get the cap back on, especially if it's a big bottle. And then again, call me over once you've got something jotted down.